constant pressure calorimetry, measuring the change in enthalpy. And this is what we're going to do in lab today. We can measure the heat of reaction for aqueous reactions in a coffee cup calorimeter, which is literally 2 coffee cups, 2 foam coffee cups. We use 2 and nest them together because then you get better insulation. We would like this to be completely insulated from the surroundings so that no heat can get lost through the stone foam cups. But you know from drinking coffee, right, even if it's a well-insulated cup, there's going to be a little bit of warmth that gets through. So, maybe someday we'll be doing this in Yeti calorimeters, right? You can buy those things, they're just not called Yeti, but you know what a Yeti is, right? We're just going to use 2 nested styrofoam cups. This is showing a loose-fitting cork lid. We have super old pieces of cardboard with a hole in them for the thermometer. Very, very fancy and just beautiful. Instead of using a glass stirrer, we're going to throw caution to the wind and use the glass thermometer to stir. Normally, I would discourage that because you stir with a glass thermometer in a glass beaker, and the chances are good that something's going to break. Stirring in a styrofoam cup, the thermometer is probably not going to break. The biggest danger is you poking a hole in the styrofoam cup, but I think we can avoid that. The Monday people avoided that, so you guys will be fine. I hope they don't listen to this video. So there's a lid on this, but it's loose fitting. And there's a hole in it for the stirrer. And so the pressure inside this cup is the same as the pressure outside. So the pressure is going to be constant. And then we have our Q equals MC delta T equation, right? So Q for the solution is equal to the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. The solution is not the reaction. The reaction is occurring in the solution. But we can't measure the temperature change of the reactants, but we can measure the temperature change of the solution. So we're using the solution as the immediate surroundings of the reaction. So we can measure the temperature change that occurs in here. That temperature change is caused by the solution absorbing heat. The heat absorbed by the solution is equal to the heat lost by the reaction. The number's the same, the sign is different because direction, right? So Q for the reaction is Q for the solution, but times -1. Q for the reaction is Q at constant pressure, which is delta H. Now, we usually want delta H to be specific to moles of something, and so then we're going to take the Q and divide by the moles of thing that reacted. Okay? So let's do an example. The addition of hydrochloric acid to a silver nitrate solution precipitates silver chloride according to this reaction. When 50 milliliters of 0.1 molar silver nitrate is combined with 50 milliliters of 0.1 molar HCl in a coffee cup calorimeter, the temperature changes from 23.40 degrees Celsius to 24.21 degrees Celsius. Calculate heat of reaction for the reaction as written. Use 1 gram per milliliter as the density of solution, and C equals 4.18 joules per gram degree Celsius as the specific heat capacity. Right? So we're looking at 2 things here. We're looking at the solution and the reaction. And yes, the surroundings technically include the rest of the universe, but because we're doing this in an insulated coffee cup, we're going to ignore that small bit of loss through the styrofoam cup. So the energy that's lost by the reaction is gained by the water, the solution, and it gets reflected in the temperature going up. So we can calculate Q for the solution. Because Q for the solution is equal to the mass of the solution times the specific heat capacity of the solution times the change in temperature for the solution. We either have those things or we can figure them out. They gave us the specific heat capacity right here. Here are the two temperatures, so we could calculate the change in temperature. Delta T is T final minus T initial. So the final is 24.21, and the initial is 23.40. And I think that comes up to 1.8. Yeah, 24.21. I'm remembering a different problem. Minus 23.4. 0.81. Bless you. That's the change in temperature. So we've got C and we've got delta T. We need the mass. They didn't give us the mass. But they gave us volume information and density information. What's the total volume here? This is 50 milliliters and 50 milliliters, right? 50 milliliters plus 50 milliliters is, wake up, 50 plus 50, 100, thank you. I can convert volume to mass using density. I can convert mass to volume using density. Please, please, please don't get out that equation. This is dimensional analysis. I want grams, so I divide by milliliters. Milliliters cancel out. This tells me where to put the number, because this time it doesn't matter, but it's 1 gram per milliliter. 1.00 grams per milliliter. So this is going to weigh 100.0 grams. Okay? So that's the mass of the solution. So we can calculate Q for the solution. It's 100 grams times 4.18 joules per gram degrees Celsius times 0.81 degrees Celsius. Grams cancel, degrees Celsius cancel. 100 times 4.18 times 0.81. So this is 338.58 joules. Let's think about the sign. The solution went from 23 to 24 degrees. The temperature went up. That means it absorbed energy or lost energy? It absorbed energy. If it absorbed energy, then Q should be positive, right? And it is. Good. Q reaction equals negative Q solution. Just -1 times Q solution. You're going to have to do stuff like this in lab today, and you're going to just like freak out about this, and then you'll feel weird later because it's just changed the sign. It's not complicated, and yet it's hard to understand. So this is just negative 338.58 joules. It's like the money thing, right? If I give you $10, that's -10 for me. What is it for you? +10. How did you get that? You just changed the sign, okay? So the solution is getting $338.58. So how much is the solution changing? It's losing $338.58, right? Minus. So we found Q for the solution. It wants delta H for the reaction as written. So the reaction is written for 1 mole of silver nitrate. This particular example gave us minus 338.58 joules. How many moles of silver nitrate was that, though? Was it 1 mole? No. We have a molarity and a volume. 50 milliliters is 0.0500 liters. So 0.05 liters of the solution times moles over liters, and it's 0.1 is 0.00500 moles. That's moles of silver nitrate. It's also this amount of energy for the HCl. Here, the HCl is the same volume and the same concentration, and they have the same coefficients. So this is one of those rare situations where we put in just the right amount of both. We don't have to worry about limiting reactants here. So it's this much energy for 0.005 moles. We want to know how much energy for 1 mole. So we're going to take, basically what we're doing is we're taking Q solution and we're dividing by N, the number of moles. So we've got minus 338.58 joules, and I'm going to divide by the number of moles that reacted to give that. Six 7716 joules per mole of silver nitrate. What should the sign on that be? Got a negative number divided by a positive number. This should be negative, because the energy is released when this reaction occurs. So that's an answer. Normally a big number like that we'd put into kilojoules, and it's supposed to have 3 sig figs. And so delta H for this reaction is equal to negative 677 kilojoules. Any questions? Negative 68. What'd they screw up? Okay, I see what I did wrong. I did this conversion in my head and I was sloppy. Moving the decimal point 3 places, 1, 2, 3 would be 67.7 kilojoules. Yeah, it should only have 2 significant figures, right? As I screwed up again. Is this temperature change is only 2 sig figs. So does that mean I'm an idiot and shouldn't be doing chemistry? No, it means I'm human, right? You guys make mistakes too, and you just have to get over it and go on, right? We all make mistakes. It's part of being alive. There, minus 68, okay. The same reaction, not the one we were just talking about, but the same reaction with exactly the same amount of reactant is conducted in a bomb calorimeter and a coffee cup calorimeter. So we've got the 2 different kinds of calorimeters, and we've got the exactly same reaction and the exact same amounts of stuff, right? one of the calorimeters we get Q equals minus 12.5 kilojoules, and the other we get Q equals minus 11.8 kilojoules. Which one did you get from the bomb calorimeter? And we're going to assume that the reaction had a positive volume change. Well, in the bomb calorimeter, we have constant volume, right? And so the change in energy is equal to Q at constant volume because the work is 0. Over here in our coffee cup calorimeter, the volume can change, but the pressure's constant. So delta E is Q plus W. Here, well, actually, let's backtrack here. This is Q plus W, which is Q minus P delta V. The delta V is 0, and so E is equal to Q. Here, we've got Q plus W, Q minus P delta V. The pressure is not changing, but the volume is a positive number. So that means that this thing here is greater than 0. And we're going to subtract that from Q is going to equal the actual energy. But when we measure this, we disregard the work. And so we think we're measuring delta E by measuring Q, but it's off a little bit, right? So the most correct one is from the bomb calorimeter, and the not quite as correct one is from the coffee cup calorimeter. But how do we figure out which one is which? Delta V is a positive number, so P delta V is a positive number. So Q minus this, what we're going to measure over here, is smaller, right? Because we're measuring, we're only measuring Q, we're not measuring Q and W. So the bomb calorimeter one should be the 12.5. Did I put the answer for that one? I didn't. So that's something that's good to think about, but that's not a critical thing there.